Thank you again for joining us today in this webinar, in which we're going to be presenting and providing you as much detail as possible regarding the signal integrity extension powered by Ansys. So before I begin, I would like to share our safe harbor statement. This is just to let you know that we are going to be talking about signal integrity, and signal integrity is currently available, up and running, and you could actually test it or purchase it right now. But I just wanted to put the safe harbor statement because there's a small chance that we'll be talking about future enhancements that we're going to be doing into Fusion 360 electronics and most probably into the signal integrity. But we're not really sure when that's going to happen. So we just want to make sure that you don't base your decisions on the future right now, base your purchase decisions of Fusion 360 electronics on something that we're working on. Okay, so that's why I brought up the statement really quick. Okay. First of all, the whole idea of, and I remember asking this to Matt not too long ago, actually a long time ago, shortly right before AU 2021, I asked him, what's going on, Matt, in regards of a signal integrity, that this whole analysis that you said, and Matt tells me, and I was a little confused in the beginning because I didn't know what he was working on. Said Fusion 360 extension using Ansys gives PCB designers immediate feedback about electromagnetic trace characteristics during the routing process. And why was I a little bit maybe a bit confused, is because for me, signal integrity, that type of simulation was always a post-process. So I didn't really get it at the beginning when kind of Matt brought this up. So let's go ahead and talk about who's joining us today. With us today, Matt Berggren, Director of all things electronics for Fusion 360, Tinkercad, and other areas of electronics. So thank you, Matt, for being here. Also with us from Ansys is Juliano Mologni. He's currently the product manager over at Ansys with over 20 years of experience on computational electromagnetics. So yes, he's an authority. And then there's a guy in our chat group, is his counterpart. So thank you for being here, Juliano. Really appreciate it. Jorge Garcia is part of our community manager teams. I've been blessed to be able to be working with George for like the last 10 to 12 years, right, Jorge? Something like that. We've been working together for a long time. And then I'll be your host today. My name is Ed Robledo. I've been able to participate in webinars as well as other presentations and live presentations. And my background basically is from Eagle. I started with Eagle a long time ago. So let's take a look at our agenda. First of all, we're going to get some insight from, in behalf of Matt, about, what was his inspiration for the signal integrity extension? What is the signal integrity extension? And then Juliano is going to give us a presentation telling us about what's under the hood that is actually, making all this work. So he's going to tell us about the method of moments solver that is being used. And then we're going to end with Jorge doing a presentation of showing us exactly how this comes together. Okay. So, last year, sometime in summer, we put together an announcement with Matt in regards of, adding some simulation, some much needed simulation, especially signal integrity simulation into Fusion 360. So I've asked Matt to join us today and say, hey, Matt, so what exactly inspired us today to, to do signal integrity? How all this come about in the partnership with Ansys as well? Could you tell us more about that, Matt, please?
Yeah, I mean, I want to be careful to caveat everything and say that it wasn't my idea. It was a collective sort of point of view between all of us within the classical kind of Eagle development team at Autodesk, and with the integration in Fusion, those people on the Fusion side of things, and then really foremost with Ansys and people like Juliano and the staff over at Ansys. Foundationally, there was a fundamental problem, something that I've wanted to solve, right? I've taught university coursework in electronics and electromagnetics and circuit analysis. And so much of what we hear in sort of pop culture for engineering is signal integrity, signal integrity, signal integrity. But so much of that, like you mentioned, Edwin, is a post-process. It's something, well, I'm going to run this after the fact. And as we were discussing with the team at Ansys, the thing that became evident was, there's really multiple layers to signal integrity analysis. And we have spent a lot of time sort of ignoring the need for signal integrity on the Eagle side of things. So we've had some integrations with various signal integrity tools. And foundationally, the tighter coupling between signal analysis, signal integrity, circuit analysis, your classical kind of SPICE simulation, and things like design rules. If you think of every EDA application on the planet expects you to go from a circuit-minded view of a problem to a geometric view of a problem. Simplest example is the distance between things. What are we talking about when we talk about the distance between copper features? We're talking about the capacitance and the electromagnetics that are hovering around the signal path.
So, since you're bringing it up, why don't we go into, what is signal integrity, Matt? What do you think? I think it's a perfect scenario for it. What do you think?
Yeah. So, signal integrity, and we can hang at this point in the slide for a second, Jorge. Signal integrity is the thing that defines the physical characteristics of the signal in the PCB environment. It is the thing that isn't a part of that highly simplified capacitor model. And instead, you do have in that capacitor model a whole host of things that maybe you didn't know about, things like insulation resistance, the equivalent series resistance of the capacitor, the series inductance that you would have on the leads or lead inductance, and the plates themselves have an inductive property. You've got dielectric absorption. All of those things, they are characteristics of a capacitor that in a highly simplified view of a circuit, you can have an outcome that looks idealized. And that's oftentimes what you get from SPICE simulation. Signal integrity is factoring the board into the equation. And going back to kind of the comment that I was making earlier, this difference between geometry and circuit analysis, effectively, did you capture mutual inductance, lead inductance, the various stack up of the board? So the image on the left, you can see just a simple 4-layer board stack up. In that four-layer board stack up, I can guarantee that the size of the plate that is the internal plane is bigger than the size of the plate in any capacitor that you have on the PCB. That capacitance is the defining characteristic or one of the defining elements, oftentimes more crucial than things like inductance in calculating an accurate impedance. And, I saw some of the poll questions earlier related to, how do you calculate these things? Online calculators are good as a general concept to sort of point you in the right direction for a highly idealized version of the board, but they would be, for all intents and purposes, kind of the SPICE equivalent. They're idealized. And I think so much of what we are trying to drive on the signal integrity side is how do you get your eyes into the PCB?
Thank you, Matt. Yeah. Excellent. I don't see any questions. If there's any questions, please use the Q&A. Matt, thank you for that. Anything else before we go forward?
No, I was just going to say, those two components on the right, they're sort of the professional's view of it. And I think what we really endeavored to do as a part of this partnership with Ansys and everything that we're moving toward in the way of signal integrity is intended to bring this all back down to planet Earth for the rest of us.
Okay, correct. Which goes back to that opening statement I had, exactly what you told me. Even though I didn't understand it then, now it's coming to fruition. So thank you, Matt, for that. I really appreciate it. Now, I'm going to go ahead and move over to, Matt, if you don't mind, I'm going to go over to Ansys now. And let's talk to Ansys. And we're using the method of moment solver. And we have the special guest with us today. Really appreciate Juliano taking the time and joining us. And, tell us a little bit about the solver and how is all this working under the hood. So, Juliano. please
Sure.
take over. Thank you.
Absolutely, Ed. Yeah. But first of all, thank you very much, and thanks for the Autodesk team, for the opportunity to present in this webinar. I must start in saying that here at Ansys, we're extremely excited and happy about the opportunity to put some of our technology into the hands of the Fusion 360 users. Before I go into the details of the method of moment solver, I know it's a lot of acronyms here. I would like to point it out that the technology that we are using here, that Fusion 360 is using, which I'll go into details very soon, is widely used today by thousands of companies and engineers, and help them design most of the electronics that we use today on a daily basis. There's a very high chance that the cell phone that you're using, the car that you're driving, the computer that you work with was designed using this technology provided by Ansys, which is now available in Fusion 360 through the Signal Integrity extension. Regarding the technology itself, I know there are lots of acronyms here, but let me try to explain what we're extracting from the design and what we are computing. For geometries like PCBs, if you take a look, there are layer geometries. We can use several numerical techniques to extract electromagnetic outputs, such as resistance, inductance, capacitance, S parameters, you name it, right? For this particular type of geometry, we learned through the years, we have the expertise and the experience that there is an approach that provides extremely accurate results in a very short period of time, almost real time. And that's the technology and the workflow that we're using here in the Fusion 360 Signal Integrity extension. The methodology that we use is to extract the cross-section of each segment of the nets. So you have the nets, they're all routed, but if you take a look at a straight segment, what we do, we create a cross-section, and that includes all the geometries, right? The signal nets, ground and power plants, all the dielectrics in every single layer. Once we have the cross-section, which is a 2D geometry, we use the method of moment solver to compute RLCG, time delay, characteristic impedance as a function of frequency per unit length. Since we know the length of the segments, based on the design that we have in Fusion, the overall calculation, becomes very easy. But going to the details of the method of moments, this is a frequency domain method. And in our case, it involves the projection of an integral equation into a system of linear equations by applying a boundary condition. What we do, in other words, is that we use MASH, a discretization, just like what we do in other numerical techniques, like finite difference and finite element methods, to represent the geometries of the traces and the planes and the dielectric layers. Then we compute the output as a function of frequency, including all the electromagnetic effects, including skin depth, losses due to the dielectrics, and of course, coupling between the multi-conductors that you have in that cross-section. Here we have some very nice plots, and what they're showing in here is actually the vectors of the magnetic fields, right? On the bottom, you see for two different, what we call modes, odd mode and even mode. And those are for inner layers, for strip lines, right? So we also have what we call a modal decomposition as part of the solution. We also have a parallel plate mode, that includes the effects of all the planes in the interaction between the planes and the traces. One of the most important output that we have from this solver is the impedance of the traces, like Matt was saying, right? It's very important to control the impedance, and not only on RF lines, let's say where you're feeding an antenna, because it's not only just real impedance, like let's say 50 ohms, but we also have sometimes to match imaginary impedance, which is one of the output of this technology. But also, take a look at differential pairs. And mostly, if you have some designs where you have discontinuity of impedance, that affects not only signal integrity, but also electromagnetic interference, right? So I think we're going to show some examples of that, especially on the next slide. But again, I'll just like to mention that this technology here is extremely accurate. It's validated by thousands of users over several, decades, and we're extremely excited to provide this technology now for all the for all the Fusion 360 users. There you go, Ed.
Thank you so much. Appreciate it. And also I asked Juliano to share with us a short video that kind of shows us that threshold between what Fusion 360 Electronics Signal Integrity Extension provides, and what, because it's a complement. They complement each other. Okay, they're not replacing either one. They're complementing each other. And I wanted to ask Juliano if he could just, give us a little explanation on a video that he has put together here. So I'll go ahead and press play, and Juliano, maybe you could walk us through it a little bit.
Sure. So this is how you access the Signal Integrity extension in Fusion. It will show in this particular case on the layout, the impedance of the traces. And there's an area in red where you have a big discontinuity of impedance. If you enable the visibility of the bottom layer, you see that there's a void, a hole in the ground plane, and that's what is causing the issue. Right? So the extension will show you where you need to fix your design. If you need more information like what you're seeing here, you can always go to Ansys. And then we're going to use different technology to solve the entire PCB to provide accurate, electromagnetic field results and some more additional signal integrity. So the extension will show you, where you have to fix while you're still designing the PCB. If you need to sign off your design, you can go to Ansys and you can compute the fields like you see here on the top of, a hotspot of electric field and even eye diagrams. So again, extension really helps you in real time while you're still designing the PCB. After you have a very good design, you can go to Ansys, to sign off your design and compute additional, electromagnetic outputs.
Thank you for that, Juliana. I really appreciate it. So
thank you.
I'm going to go ahead and move over to Jorge. Jorge, I'm going to give you control of the slides. Give me 1 second. And Jorge is going to be teaching us a little bit of what it looks like and how does it work. Jorge, please take over.
Yeah, so carry on with the previous point. I want to talk about the 80-20 rule, make the distinction very clear between what we're providing with the extension and what Ansys provides. And the 80-20 rule is very simple. You get 80% of your results with 20% of the effort. If you need something like what you're looking at here, which is a live visualization of how a signal is traveling down, in this case, it's a USB signal at about 500 megahertz. If you need this, if you need to be able to observe how impedance is changing real time, go to Ansys. But the idea behind the extension is to get you 80% of the way there. The extension is going to show you where you have impedance discontinuities, what the time delay is of your circuits, of your traces, and knowing impedance and knowing time delay, you electrically know almost everything you need to know about your signals. So with that said, I want to go over with two very simple concepts, and that'll give a little bit of context to the demo. So first off, if you have a constant cross-section, you have a constant impedance within the vicinity of the trace of interest. Now, how close is too close? That's a subject for a completely different webinar. Okay, or how close is close enough? That's for a different webinar. But let's say that within a certain proximity to the trace, as long as the cross-section is constant, the impedance will stay constant. If anything changes, the separation between polygons to the trace, if you have a gap, any change in that geometry will lead to a change in impedance. And when you're working with signal integrity and when you're working with high-speed signals, one of the key points besides the specific impedance is having it be constant. That takes us to the next point, which is that current is going to follow the path of least impedance. And without going into any sort of major detail, that path is the one that closely follows the forward current. So if we think about it, you have a signal path and you have a return path because electricity flows in loops. Both, the closer they can be, the more similar they can be, that's going to be the path of least impedance. So if you look in the first picture, there's no gaps in the return plane, and the return current can follow the forward current exactly. But if you look at the others, any breaks are going to cause that return current to have to go around the break in the plane, and that's going to change the impedance. And Juliano showed that earlier. Anywhere you have a cut in the plane, you're going to notice that the impedance there is going to change because the return current has to flow around the cut, has to go around that gap. So with these two very simple and straightforward ideas in mind, let's start showing how the extension actually works. So this next video, Ed, if you can hit play, let me know once you have hit play.
Yes, Jorge, go ahead.
Okay, you're going to notice that in this, if you have the extension enabled, you go into the simulation section. I have analyze signal. It's a panel within Fusion 360. And you define what signal you want to analyze by clicking on it. You'll notice that it filled in D_P. It's one of my differential pairs for USB. You specified the specific frequency of interest that you want to analyze impedance at. And then you can specify either a target impedance or not. It's not a requirement to specify a target. If you don't specify a target, it's just going to show you how the impedance changes along the entire length of the trace. If you do, then you'll be allowed to specify a tolerance, as you can see here. And then the results will show you how it deviates from that target impedance. So I've put in my target, I've put in a tolerance. And then when I analyze it, you're going to see that the results show how far the trace deviates. So as you notice here, the trace as it is in the beginning deviates pretty heavily. And the minimum, we have about 66 ohms, at the maximum about 86 ohms. So we're way off target. And you can see the colors indicating what areas are more off target. So the darker the color, the stronger the red, the more it's deviating. And you can see that there's specific areas where it has deviated heavily. And that's where we're going to go into the next slide. Oh, no, it's still going. Okay, so good. I thought I had finished. So you're going to notice in this one that we have a little section of orange near the top. And if you notice, we can tell because the simulator is giving you every single segment of the trace. So every single segment has been simulated. And you can see that there's certain areas where there's greater deviations than others. We have kind of two major problems. Obviously, we're off spec, but we're also not consistent in our impedance profile. So if you notice near the ends, like I'm showing here, there's kind of areas where we have big deviations, and it's because the separation is changing between the differential pairs. But we also have areas where the polygon has broken. And because of that, there's no polygon filled in those areas, and that causes the impedance to change as well. So if you look in this trace on the top northern area of it, you're going to see that it's orange, and it's because of that. So additionally, you can also simulate multiple signals at the same time. It's not like we did D_P. Now I'm going to simulate D_N, and the extension keeps track of all of these. So yes, it simulates D_N now, but it didn't erase D_P. So I can compare, I can jump between them and see the relationship between multiple traces. So it does keep history of your traces and of any analysis you do while using the extension within the session. And that's what I'm showing here, basically jumping between both traces.
Yeah, I'd only add to that, Jorge, that, you know, this was really intended to optimize this based around the workflow, based around the idea that you've run an analysis on one thing and now you want to get a view of that as it relates to something else. It's just really intended as a workflow optimization, and we put a lot of thought into the experience on this.
Awesome. Thanks, Matt. So I think this video is over. We can go into the next one.
Yeah, it is.
And we're going to show the first fix to improve impedance, which is make it constant. Right now, we have a lot of deviations. So I'm going to go ahead and switch to the next slide. If you can hit play, Ed, let me know once you've hit play.
It's done. It did it automatically, actually.
Oh, no, it's in the same
Oh.
one. So let me switch. Okay, this one, creating space for the polygon. This is the
Very
one we
well.
want. Okay, did it play? So you can see right there, those are areas where the impedance has changed drastically because the geometry has changed. It's a violation of that first slide I showed you. What are the changes? Polygon is broken there, and we have components that are near the trace there, or close to it. So that's causing a change in impedance as well. So the video is playing, right, Ed?
It is. Yes, it is.
Okay, cool. So we can see mission number one. Let's at least get it to be uniform. I'm highlighting the different areas where the impedance has changed. If we can get it uniform, then we can worry about getting it to the value we want. So that's what we're going to try to do first. So right now I'm just showing you where we have deviations. And basically what we're going to do to fix it is we're going to adjust some of the signals to try to create room so that the polygon can fill. So this design is already pretty heavily routed, so I'm trying to minimize the number of changes I'm making. But that D13 signal at the top, I have some room. So I can go ahead and move it to give the polygon space to fill. So that's what I'm trying to do with the design here. So you're going to notice as the video progresses, we're going to be transitioning at certain points to be able to show the polygon filling. So you're going to see some of the moves. It's going to speed up. And then, yeah, there we go. It's doing the thing. Cleaning it up. And now we've improved it there. So you'll notice that the extension shows that the analysis is out of date. Every time any changes made to either the board stackup or the routing or anything that could affect impedance, which is a lot of stuff, you're going to notice the extension realizes that you've made a change and will ask you to refresh the results. So you'll go ahead, you'll hit that refresh, and you'll see that the top trace, which is where the polygon can now fill, is far more consistent. So there's still areas we can improve, but you get the idea. So in this case, I wanted to just create room for the polygon. So let's go into the next slide. In the next slide, you're going to see that I've continued to fix things. So the polygon's going to have more room. And here, what we're going to do is we're going to reroute the differential pair. So part of the impedance calculation is dependent on the width of the traces. So what I'm going to do is I'm going to go ahead and reroute differential pair. That way we can deal with those gaps near the ends. If you notice, the separation of the pair changes on the ends, and that's where a lot of impedance changes. So I'm going to reroute these differential pairs, and I'm also going to reroute them at a new width. So as we know, width is a key parameter in defining the impedance of a trace. So by adjusting the width, I'm going to get us closer to our desired parameter. So right now, remember that difference. We're between 66 and 86. And now you're going to see the process of it getting routed. I created some separation from those capacitors because I want to be far enough away that they don't affect my impedance profile. And I get the polygon filled. You see the polygon is filled. And now you see the new results, and we're a lot better. We went from 66 to 86 to 52 to 69. So we're closer. We're closer to what we want, but not quite what we need it to be. So if you watch any of the training material for the extension, you're going to notice that one of the knobs or one of the parameters we can further adjust is dielectric spacing. So in this design, I could have adjusted the width more to try to get the impedance spot on, but it's already a routed design. I don't want to mess with it too much. And I also want to demonstrate this other parameter that we can adjust. So in the next video, we're actually going to use the layer stackup manager to adjust our layer stackup to reach the impedance we want to have. So let me know, Ed, when this one's playing.
Yeah, I will.
Okay, cool. So you can see we have much more consistent impedance here. And that's the case for both traces because now they have polygon on both sides. There's enough separation from existing components. So we're at least consistent. Now we're going to go into the layer stack manager. Now the layer stack manager is a harder thing to play with compared to width. So when you're changing width, no problem with your manufacturer. Changing the layer stack up, you have to make sure your manufacturer can deal with this. Otherwise, you're making a change that they can't manufacture. So if you notice, I have a dielectric here. It has a certain thickness. And what I'm actually going to do to try to improve our impedance to get it closer to what we want is I'm going to remove one of these dielectric layers. Again, we have to talk to our board house. Maybe they can do this, maybe they can't. So you want to make sure that you conform to their specifications. So in this case, let's assume it is acceptable, it is okay to do. What you're going to see is I'm going to delete that dielectric. Now my separation between the first and second layer is much less. You'll see the extension notices that has changed. We go ahead and update our results, and bam, everything is wonderful. Now we're within spec. You'll notice the range is 42 ohms to 50 ohms, which is within the 15% tolerance of the single-ended impedance of 45 ohms for USB connections. So that's it. So using all these different aspects and the simulation to verify our results, we've now, before we've committed to any hardware, we've ensured that we won't have any impedance or signal integrity problems in our design. And that's really what the extension is about. Again, it doesn't show you the fields emanating like Juliano was showing previously. If you need that, you go to Ansys. But again, 80% of the time, this will do, and this will get you much further along than if you didn't have it. Where you could lose, different, you might have to go through several respins and things like that. So thank you very much.
Jorge, that was awesome. So, we talked a little bit about what is signal integrity, and Juliano told us a little bit more about, the threshold between Fusion 360 signal integrity extension, as well as the capabilities that you have in Ansys. That way you have an understanding of how one complements on each other. And then Jorge now just walked us through what changes could you do when you use it? If you have impedance mismatches, you want to fix that. And then you have a lot of knobs, as I'm going to steal that from you, Jorge, a lot of knobs that you could turn to actually you could get the appropriate impedance on your line. That way your components could operate correctly. So what are the key takeaways today from this webinar? What is that we want you to walk away with this? First of all is, one thing I like to do, a lot of times you get the hardware done first and then you use equipment and find out that you failed. So why not use simulation? Simulation helps that first pass certification to ensure that your signal integrity and EMC is compliant. Number two is it's fully integrated. This is not a post process. This is fully integrated into Fusion 360. So therefore, as you're routing your lines, you're able to find out exactly what's your time delay, what is your impedance and capacitance, inductance, and resistance on the line as well. And these are results that could be downloaded, right? Jorge, you want to tell us a little bit about what could you do if you download all these results on your trace? What else could you do with those results, Jorge?
Yes, if you wanted to get real fancy, you could actually do a lumped element model using SPICE. But you can also take averages, do something simpler. Basically, you have the complete results of the simulation in CSV format. So you can manipulate them, do math on them, do calculations, do graphs. We give you the raw data, and you can process it then as you see fit.
So I will be sharing on the chat some videos and some links to the help files and some other resources. But before I go there, so, the new Fusion 360 and Signal Integrity Extension, which is powered by Ansys, gives product designers and engineers access to electromagnetic analysis capabilities that allow them to inspect and resolve issues with signal performance early in the design phase. So before you actually commit, you actually now find out. So let's talk about some of the resources. And I'm going to be putting these links on the chat. So first of all, the Fusion 360 help files. I talk about the signal integrity, how to use it, as well as we have a 4-part series video that Jorge put together on our YouTube channel. Excellent video, very similar to what you saw here, but a little bit more in depth. And if you want to learn more about signal integrity and the effects of it, and kind of like a parallel, how does it work in Fusion 360, we have on our blog section, and I'll be sharing all this. We have some blogs in that regards as well. We have a 4-part blog that you're more than welcome to take a look. So we're providing you all of the resources necessary to learn about it and to learn about signal integrity. That way, in case you want to dive into it, you need to add. Juliano was showing me an example yesterday of an old washing machine, and now the new washing machine needs to have Wi-Fi, has the Bluetooth and all that jazz, and all these speeds, just really old ones compared to the new one. The engineers are now subject to having to use signal integrity capabilities. So I would like to go ahead and go to the floor and let's talk. Let's answer some questions if there are any. Jorge, is there anything that we need, or Matt, or
I was just going to comment on one of the things that's come up here. Reza in the chat had asked a question about waveform views and support for IBIS and things like that. I think the fundamental thing that we really want to address is that tighter coupling, I guess no pun intended, or maybe it was intended, between the design rules, the design intent, and the sort of near real-time insights. So we have plans down the road. I won't try to speculate on timelines, but going into next year and beyond on providing something more of a waveform view, but then also a sort of a schematic extraction. So from the output of whatever the amplifier is to through a filter network and then ultimately into something else. Can I get that signal path? Can I extract the RLC properties of that signal path? Can we construct a transmission line model? And then I think one of the things that you'll find is pretty much universally true for anything other than, like, say, spice simulation from somebody like Ansys, is most spice simulators can do a single lossy transmission line model, but what they can't do are coupled lossy transmission line models. They can't do bundled lossy transmission line models. And so a lot of what our efforts are going to be around is extracting the right information for those bundled lossy transmission line models as waveforms, and then subsequently getting that transmission line data for single-ended signals, differential signals, into a format that you could use in normal kind of circuit analysis process or techniques. We are putting a lot of thought into it. So feedback related to that is fantastic. And if people can help us to prioritize the backlog for those things, it would be super helpful. My team is super committed, and the folks at Ansys have been exceptional throughout this process. We want to be sure that we get it right. But I think the most important thing for us is to help you to get your eyes into the board. I'll make one other quick comment related to that, Edwin, just for Jorge.
Please.
The shout out to Jorge and his video. He actually does a video that he extracts the transmission line characteristics, brings it back into schematic, and then runs a spice simulation on it. And I would look for that from him. It's number 4 in that series, but it's pretty slick. And it was everything that I had hoped somebody would do.
Well done, Jorge. Excellent. So thank you for that, Matt. So I wanted to go back to Juliano and ask him if you had, well, we're answering the questions on the Q&A as well, but I want to go back to Juliano. Any final thoughts or of the questions that you've been seeing, Juliano, on the chat as well as the Q&A? Is there anything there that you would like to go ahead and address, please?
Yeah, absolutely. I see many questions here, regarding the difference between this solution and Ansys. So I think what we're trying to do here is to provide Ansys technology to Fusion 360 users that are designing the PCB. If you want to simulate in Ansys, you're going to have to understand a little bit about simulation. You're going to need to learn a new tool. You're going to need to learn, a little bit about numerical methods. It is not as easy as just click a button and see the results like Jorge was showing here, right? And that's extremely valuable information. I think, the whole purpose of providing this technology is to actually get you to the right design, right? If you want to, of course, you can always go to Ansys, but it's a different platform. You're going to need to understand a few different things, right? It's not as straightforward as just click of a button like we saw it here. So I'd just like to point that out. I mean, having this kind of information almost in real time as you're changing the layout of a PCB is extremely valuable.
Thank you. Yeah, because usually it's more of a push process. So you gotta be going back and forth and things
exactly.
Like that. So, excellent. Thank you. Appreciate it. Jorge, was there anything else that you wanted to address from the Q&A? I saw that you wanted to answer something live. So please. You're muted, Jorge, just to let you know.
That's how Zoom works. So we have a question from Jeffrey Viviani. So in this case, Jeffrey, it's looking at copper. It's the fact that there's another piece of copper near the trace or close enough that it will affect the impedance. So it really isn't concerned what the specific value of the component is. It's the fact that there's a piece of geometry there that's near enough that it's going to affect the impedance of the trace. Whether it be a resistor or capacitor, for the purposes of the signal integrity simulation, the impedance of that trace, it doesn't matter. It's just the fact that there's now another element that can couple, as Matt was mentioning, either capacitively or inductively.
Okay, thank you for that, Jorge. Well, we went over by 2 minutes compared to what the intended amount of time that we have. We are going to be taking this video and uploading it up to YouTube as soon as possible for those that wish like to go ahead and review what we talked about it. Big thanks to Juliano for being here, our special guest, Jorge especially, and Matt. Really appreciate always your insight and joining us today from your busy schedule. Thank you so much for being here. Everybody, Thanks for everything. We hope that this really enhances your design experience in Fusion 360. Please use the resources that we provided you. And those that are questioning about the pricing and how to get it, please watch the videos that Jorge made. Plus, take a look at the links that I provided earlier in the chat. You could get detailed information on that as well. Thank you, everybody. Thank you all. It's been a pleasure. And the partnership with Ansys has been phenomenal and will continue to grow. So everybody have a great day and thank you for everything.
Yeah, thanks everyone.
Bye everyone. Blair,
Bye-bye.
it is a free trial. It does have a trial.
There is a 14-day trial. Yes, that's correct. Thank you. All
Thanks,
this and more with Fusion 360.